Yep. Okay. That'll show better this way. Yeah. That's good. So the next exam is just on this one topic, gases. I think in your textbook is chapter 10. All right. Gases. We all have sort of an intuition about gases. Owing partially to the fact that we breathe one all the time. They're rather tenuous, you might say. Where is it? Just maybe barely feel it when you move your hand. Unlike if you slap something solid, you feel it pretty good. And that's owing to the fact that the particles in gases are very, very far apart. And the forces that you feel on your hand are proportional to the number of impacts of particles on your hand. So, and I guess that's a good thing, but otherwise we wouldn't be able to fly airplanes very fast. Although there's considerable work in the water transport, especially weapon systems, at very high speeds. But they use modifications to the torpedoes that create a cavitation around. So it's like it's in water, but it's really traveling through gas. It's kind of strange that way. The reason we say gases are semi-independent is the ideal gas is one in which all the particles act independently, as if they're just tiny little billiard balls. And occasionally they smack into each other, but they don't interact at all. That's an ideal situation. But the truth is that gas molecules do interact. Sometimes they repel, sometimes they attract. But under certain conditions, they can be treated as if they're ideal. So they're moving very fast. In fact, there are some calculations that can be done, and I think, I'm not sure if we do them I think it's in this lecture, toward the end. Yeah, toward the end we do a calculation where the average speed of a gas molecule, it's really high. It's something you wouldn't expect. And gases can be made up of either independent atoms, like for instance, noble gases. They can be made up of molecules like the diatomics, hydrogen, nitrogen, oxygen, so forth. Or they can be made up of more complex molecules, like sulfur dioxide. You'll know that one when you smell it. Another characteristic of gases, this is an archaic word, miscible. It just means when you mix two or more gases together, they always form a homogeneous mixture. They're miscible in one another to infinite proportions. And that's owing almost exclusively to the fact that there's so much space in between the molecules. There's room for everybody. So when you mix two gases together, you get a solution. They do have mass, owing to the fact that every form of matter has mass, but they just don't have a lot of it. And they're spread out so far that the mass of a given volume is a very low number. The density is extremely low. But they do have mass. Consequently, any moving mass has kinetic energy. And it's just as valid for atoms and molecules as it is for large things like cars and buses, that the kinetic energy is proportional to the mass times the square of its velocity. And this will come out in joules. As long as the mass is in kilograms and the velocity is in meters per second. So square that. But while we're here, if you resolve this in just the units and without numbers, kilogram meter squared per second squared is equal to a joule, in case you ever have to do a conversion. But gas molecules do have kinetic energy, and as a consequence, they're moving very fast, and they have this energy. So when they strike the walls of their container, which they have to have, gases have to have a container, and they expand to fill the volume. When they strike the walls of the container, you can measure that as the pressure of the gas. We have to assume that their motion is random, and primarily because there's so many molecules, even though they're really far apart, just a small amount has a huge number of particles in it. And in order to track each particle, you'd need 1,000 supercomputers, and then you probably wouldn't get it right. So we just assume that their motion is random, but we know it's not. Because if we could track every particle, then after every collision, we'd know exactly where it's going, based on physics. But for chemists, that's not quite as important. Most chemists. Physical chemists, they're kind of weird. So what about the nature of gases? Well, in order to describe gases, the early chemists chose gases to study because they exhibited this ideal behavior. In other words, one gas is just as good as another, as long as it's at 1 atmosphere pressure close to it and room temperature. And under those conditions, we now know that that corresponds to low pressure and high temperature. Low pressure relative to, 100 atmospheres, right? That would be high pressure. 1 atmosphere is low pressure. And high temperature is relative to what? Well, relative to absolute zero. It's room temperature is like somewhere in the neighborhood of 300 K. So under these conditions, most gases behave ideally. Trouble is, I haven't defined what ideal means yet. Not really. I mean, I've alluded to it. So these founding fathers of chemistry began studying gases first because they had the instrumentation, the technology to do it. In addition to the fact that every gas seems to behave like every other gas. So you could study any gas you wanted to and come up with the same laws. And that's how they started out with gas laws. They just described how the gas behaved under certain conditions. And they found that if you know these 4 factors, you can describe the behavior of a gas. You need to know the pressure on the gas. You need to know its temperature. You need to know how much of it is there. We now designate N for moles. That's how much there is. And volume. What volume does it occupy? Now, the other one that we don't have up here that comes into play eventually is mass. But it turns out the mass doesn't matter for the gas laws. The gas laws are perfectly independent of mass, as long as you know these 4 factors: pressure, temperature, volume, and moles. So how much of it there is. Okay. So we are interested in gases. Earth's atmosphere is a perfect example. And it turns out to be a solution, primarily of nitrogen, but there's some oxygen in there, fortunately. And then that makes up about 99%. That's oxygen and nitrogen. And this is 79%, and this is about 20%. The other 1% is primarily argon, the noble gas. But the little bit of discrepancy in here, what we might consider error, is room for a bunch of other gases. Right? So you're going to have carbon dioxide in there. You might even have some, that's the lion's share, carbon dioxide. But of course, since Industrial Revolution, there have been some other things injected. Of course, natural sources, cattle produce lots of this, methane. And then, of course, we've injected a bunch of stuff other than that. Well, I left out water vapor. Okay, that's a major component. In fact, as far as greenhouse gases go, not the intrinsic value of water, but the fact there's so much of it in the atmosphere has a massively huge effect on trapping heat in the Earth's atmosphere above and beyond carbon dioxide. This is, I look at carbon dioxide and the hysteria that surrounds it as more like, pay no attention to that man behind the curtain. The wizard's pulling the knobs and things. It's a way for certain groups of people to direct your attention elsewhere. Anyway, so obviously the atmosphere is necessary for life. For heterotrophs like us, we need the oxygen. But for autotrophs like green plants, trees and grasses and so forth, the oxygen is a pollutant. They'd rather have CO2. That's their food. Okay, I'm not going to spend a lot of time on that. Pressure. Pressure in addition to volume were the first 2 factors that were very easy to quantify. Okay. So all we need is some units of pressure and a way to measure it. Right? So that problem was solved by an Italian by the name of Tortelli, okay, when he invented the barometer. And he used mercury to do it. He noticed that if he had a vat of mercury, which would go this direction, the meniscus of mercury goes the opposite to water, and he took a long tube that was closed at one end and filled it up with mercury and then stoppered it with his thumb. And then he submerged his hand in the mercury. He didn't know about toxicity then. And released it. Then this tube with an open end down, closed in at the top, which was filled with mercury, now has dropped. Right? So you got mercury all down through here and in here, but there's nothing up here. So when he did that, he created the first vacuum, which just means there was something there, now there's nothing there. That's a vacuum. But he wondered what was supporting it. You know, because I mean, there's got to be something holding it up, because mercury is very heavy. So he reasoned that the air pressure was bearing down on this part of the mercury, and the force is being transferred here to hold that column up, because there's nothing pushing down on it here. Right? You open the top of that, then you got the same pressure pushing down here as you do here, and it just stays level. But if there's nothing pushing down here, because there's a vacuum there, then there's no force to balance it except for the weight of the mercury. So, and he noticed that if he threw this in the back of his ox cart and went up a mountain, this thing dropped. And if it went from Rome to the sea, the elevation, he's getting closer to sea level, the level rose. So he reasoned that all this air above his head has mass, and it's bearing down on that mercury. And you can measure the air pressure in terms of how tall that column is. Okay, so turns out that it was, in terms of millimeters of mercury, at sea level, now we take 760 millimeters of mercury as 1 atmosphere. So sea level is the standard, that's 1 atmosphere, and this is the height of the mercury column that corresponds to that 1 atmosphere pressure. So notice you've got an equivalence here. You can form a conversion factor, right? So if you have something in atmospheres, like that, you can convert it to millimeters of mercury using that equivalence. Okay. There you go, 1643. Well, these guys are getting pretty active in the 17th century. So once we were able to measure atmospheric pressure, it didn't take long for scientists to modify this design to measure pressure of gas trapped in a vessel. Okay. And other modifications we've used. You ever been to a doctor's office that has one of those things on the wall? It's a Mercury Stigma Manometer. It's based on this principle, except that this is closed here, and there's a tube that goes to the cuff that goes around your arm. So as your pressure changes, presses down on this, and that thing goes like this. That's the way they measured it originally. And then they went to modifications with a diaphragm inside. Do it manually. Now they don't even do it manually. Just wrap that thing around and push a button. I don't trust them. I'd rather do it myself by hand. Anyway, so this is Tortelli's barometer. And it was, as they say, all the rage. You could measure pressure. They used it for weather very soon after this, because they noticed that when bad weather was on the way, you noticed the pressure started to drop. And then as the weather passed over and it started getting nice weather again, pressure would go back up. It's always been that way. Low pressure signals bad weather, high pressure signals good weather. Okay. Let's see. Come on. Here we go. So there's your sea level atmospheric pressure at 760 millimeters mercury. They've also created another unit. Called the torr, in honor of Tortelli. It's just 1 millimeter of mercury equals 1 torr. So when you see torr, just think millimeters of mercury. This is just illustration in the airport in Raleigh County, Beaver, where I'm at. The pressure is going to be less than 760, simply because of our altitude. And Beckley, we're about 2,600 feet, something like that, half a mile. And it's enough to decrease the pressure. Pilots need to know these values. In fact, before they take off, they land, before they take off, they check with the tower and get the local air pressure, and they set that to this elevation. They should be sure this matches the air pressure at that location. And because altimeters in the airplanes are air pressure based. In fact, I've seen study, you would think that GPS on a plane, and they haven't, right? But a GPS is less accurate for altitude than the old style air pressure altimeters, barometric altimeters. They're more accurate. Of course, they can't tell you where you are in this direction, but that, they're better. Okay, so if we change this to atmospheres, you just need that conversion factor. And there's your atmospheres at the Beckley Raleigh County Airport. Winter place is a little higher, so its pressure is going to be lower. So it's, what was it? 0.88. Okay. Now there are standard units of pressure that are accepted in the SI system, the international system. And the reason they want to use this type of standard pressure, the Pascal, that's named after a Frenchman who was a polymath. He did all kinds of different stuff. The reason they want to use this version or this measure of pressure is because it's based upon other fundamental units, right? 1 Newton of force per square meter is a Pascal. That way you can change back and forth. The measure of millimeters of mercury, I mean, what does that mean? You need a conversion factor, and there are, I mean, now we have them that you can convert to Pascals, but if you want to do any conversions into fundamental units, then you've got to go to Pascals first before you can get there. So these are other possibilities. If you're measuring the pressure at 1 atmosphere in inches, is 29.92 inches. Okay? If you're measuring in PSI, or pounds per square inch, it's 14.69. So those are all possible conversion factors where this is equal to that or that's equal to that. The barometer on the wall in my lab at New River reads off in inches of mercury. So if we want to do any calculations using atmospheres, we have to convert.
So we need to really confine ourselves in any of those.
Maybe these two. There might be a question in your review document using Pascals, but the information should be there in the useful on the last pages.
Okay.
Yeah, it should be there, those conversion factors, so you don't have to memorize them. A bar, there's another unit. The bar is this many Pascals. We used to have an instrument called a freeze dryer. Actually, the fancy name was lyophilizer. And we would draw the pressure down in that to near vacuum. It would be like 10 millibar pressure in there. That allowed water to sublimate from the ice in our samples directly into a gas and be drawn off. What that does is it prevents the damage of cell structures in our samples. Okay. So these are different ways that you can convert. If we want to go to PSI to inches of mercury, you can chain your conversions together. Right? Atmospheres cancel, PSIs cancel. You can convert. I think that should be equal to 1 atmosphere. Oh, yours is 1 atmosphere. Okay. 1,013 millibars is 1 atmosphere. Okay. I was hoping we'd get to laws here pretty soon. We won't spend a whole lot of time on this stuff. This brings out the, okay, this makes the point. Tortelli could have used any number of liquids in his barometer. I mean, once he decided that, he observed that the forces of air could suspend a column in a tube like that, he could have used water. I mean, water was fairly common. Problem is, water is less dense, 13.5 times less dense than mercury. So that means the column suspended would be about 33 feet tall. Right? So nobody wants to blow a glass tube 33 feet long, much less carry it around. So he used something denser, and mercury was very well known at that time. Alchemists have been playing with it for centuries. It was easy to come by. So he rightly chose mercury. It's the densest liquid that they had available to them at the time. Okay, laws. First law of interest is Boyle's law. And purple's wearing out, so we'll switch back to green. Blue. Boyle's law. Boyle's law describes the relationship of a gas between pressure and volume. What Boyle noticed, and he used a modification of Tortelli's idea. In fact, instead of creating a vacuum, he actually trapped the gas in a tube with only one open end. Right? So he used a J tube. So he had, let's see, like this. That. Open at that end. So in here, you started adding mercury. So it would pool up here and then get there and there and there like that. Once it touched this inner surface, that gas was trapped. And then he could just keep adding mercury. Right. Initially, there was really no difference in the heights. But the more mercury he added on this side, that probably needs to be a little smaller. The more mercury he added on this side, the less of an increase he saw on this side, because he was getting pushback from the trapped gas. So the measure of pressure on that gas was the difference in this height to, say, let's take it up to here. It would be maybe down here. So the difference representing the pressure in millimeters of mercury on that gas is this difference here. Okay, so that's how he measured his pressure. Okay. By the way, he had this, plus he had another barometer, and he measured the atmospheric pressure. So he added these two together. The atmospheric plus this difference was the total pressure on that gas. Okay. So then the volume then was from here down to here. So he had this pressure over here, and that volume. And he noticed that as he kept adding mercury and getting these pressure differences, the pressure increased. And then he got this value, but the volume was decreasing. So they're inversely proportional. That means one goes up, the other goes down. He also noticed that if he took the pressure values and multiplied them together at each step, they were always equal to the same value, a constant value. Okay? So there's another clue. Anytime you have a product of variables equal to a constant, you have an inverse relationship. This is fixed. That means if that goes up, this has to go down. So this was Robert Boyle. And when you plot the values, here we go. Got another one? Yeah, there we go. So this atmospheres times this volume equals that value. That one equals the same value. This is the constant. And if you keep plotting them like this, you get a curve, right? It's a special kind of curve. It's called a hyperbola. And of course, if I haven't said it before, scientists hate curves. Whenever we can get a straight line, we're going to make one, even if we have to modify the data to get it. Okay, so this was Boyle's law. P times V equals a constant. P times V equals a constant. And plotting gives you a hyperbola. So how do we get a straight line out of that? Well, what we're looking for is y equals mx plus b. So we need a y equals a slope times an x plus b. Sometimes b is 0 for the origin. And how are you going to get it out of that one? Well, what if we say divide through the whole thing by v? So then p equals k over v. If we factor out v and leave the k constant, there you go. Y equals m. Slope of the line is constant, m times x. Y equals mx. And plus b here, that's 0. Goes to the origin. So if we plot 1 over v, the inverse of v in each case, just take the inverse of this one. So the inverse of 4 would be 0.25, 0.2, 0.1, what was that? 1 divided by 20, 0.05. Plot those values against the pressure, then we should get a straight line. We'll have different units here, because this is volume. So we'll have 1 over v units here, different than those. But when you plot these against those, you get a straight line with a slope k. We have, I think we have not this next lab, but the one after that is Boyle's Law lab. Okay. The other thing you can do is, if you have a trapped gas and you do something to it, like you change the volume or you change the pressure to watch what happens to the volume, then the first condition is equal to a constant, right? Well, the second condition, your new pressure and your new volume are equal to that same constant, aren't they? So the commutative property says if A is equal to B and B is equal to C, then A is equal to C. So you can just write it this way. Okay. So now, as long as you don't add any more gas, oh, and by the way, for all this that's happening, you have to keep moles constant. Can't add any more gas to it or take any away. And temperature is constant. Because temperature will have an effect also on pressure and volume. So those two have to be constant in order for this relationship to hold. And that's true for any of the other laws. If we're going to look at relationships between any of the other variables, the ones that aren't being studied have to be constant. Okay. So the trick in solving an equation like this, where you have before and after conditions, is knowing which one's before and which one's after. So it's important that when you encounter a word problem, that you set up your little table and identify what's what. Then when you put it in your formula, you know it's going in the right place. Okay, that's Boyle's law. And this is an example. Notice also that, I shouldn't have erased that. That you can form ratios here. So if you have pressure measured in some other value besides atmospheres, then you don't have to change them. Because they're the same on both sides, they will cancel. Same for the volume, right? So instead of liters here, maybe we measure the volume in milliliters. Instead of millimeters of mercury, we measure this one in atmospheres. Or you can measure something else. It doesn't matter. But in this before-after scenario, you only need one unknown. If you have one unknown, you can solve the problem. Okay. And it's your choice whether you want to leave it like that, plug the numbers in and then solve, or solve for your unknown first and then plug in the numbers. It really doesn't matter. You get to the same place eventually. Oh, here's one in cubic feet. Right? Doesn't matter. Unless, let's say, this is your initial volume and initial pressure. So if you squeeze it to this volume, what will be the pressure? If you're solving for V2. If you want the pressure in atmospheres, then you solve the problem for PSI, then convert it to atmospheres. Okay, next one. Charles' law. Boyle's was English, Charles was French. Okay. Charles investigated the relationship between volume and temperature. So that means that moles and pressure are constant. Okay. Now, Charles came quite a number of years after Boyle's. let's see, yeah, 1787. Charles, he's in the 18th century, Charles was in the 17th century. The reason it took so long to investigate temperature with volume is that they didn't have a good thermometer in the 17th century, a way to measure temperature. Once that thermometer was invented, the mercury thermometer, and the scale to go with it, then they could start investigating temperature relative to other factors. So what Charles found was that as you increase the temperature, the independent variable, the volume increased. That's with everything else constant. Pressure's constant, moles are constant. So how do you do that? Well, good example is you have a cylinder and there's a movable piston in it right here. So your gas is trapped down here. And there's a fixed mass bearing down. You could use atmospheric pressure, or you could add some weight to it, like a couple of kilograms. But once you establish that force, you can't change it. Pressure has to be constant. So now you just put it in a bath of some kind and change the temperature and watch what happens to the volume. So when he plotted his data, he found that you got a straight line. Okay? So the relationship there is volume divided by temperature is a constant. Because if this is constant, when this one goes up, that one has to go along with it to keep this one constant. So the quotient ratio of two variables is always a direct proportion. It's already a straight line, so we don't have to mess with it. The other thing that's peculiar about the gas laws, about actually any calculation in chemistry or physics, is the temperature has to be in absolute terms. So for our purposes, that's Kelvin. Okay. Remember, we talked about, did I do that discussion with Kelvin yet? No, I'm going to do it now. Where did Kelvin come from? Right. Up to this point, we had degrees Celsius, was a metric system, and we also had degrees Fahrenheit, which is commonly used still amongst meteorologists. And the relationship is just 9/5 degrees C plus 32. Or your book might say 1.8. The same thing. So you can convert Fahrenheit back and forth. And Kelvin, which is just K symbol, it doesn't have a degree mark, is equal to degrees C plus 273. Okay, and I'm going to show you why in a minute. So if you graph your data like this, notice you get a straight line, but at 0 degrees Celsius, this gas has a volume of 1 liter. Right? So Kelvin, Lord Kelvin, said, wonder what would happen if we just, keep decreasing the temperature, right? For an ideal gas, he reasoned, we ought to get to some point down here, the temperature is so low that we got no volume, right? It was theoretical. So he just extended the line until it intersected the x-axis. So the x-intercept, like that, is where Lloyd Kelvin said, that's our starting point. So he said, and the advantage of Kelvin is that all the Kelvin temperatures, the values are positive. There are no negatives. So you don't have to deal with signs. And it turns out that this is on the centigrade scale, in Celsius, is minus 273 degrees. That's why you add 273 to this one to get Kelvin. And so at 0 degrees Celsius, that'll be 273 K. So whenever you're dealing with, I chopped off the last 2 decimals. We don't need them. Whenever you're dealing with temperatures calculations in chemistry, you have to use absolute values, and that's Kelvin for the metric system. Okay. A similar transform can be made for volume and temperature. So if you have before and after, right, V1 over T1 equals V2 over T2. And you just have to be sure that this is in Kelvin and that you put your values in the right place, before, after. Okay. I don't want to beat that horse too long. So in this case, we converted Kelvin 25 degrees to 298 K. And this one, 300 C to 573 K. And the volume is 50 liters, so we're solving for actually V2. And we find that if we increase the temperature from basically room temperature to 300 centigrade, we'll increase the volume from 50 liters to 96 liters. Now, these laws they work for any gases as long as it's, relatively speaking, high temperature, low pressure. So we can use these laws to study chemical reactions as well, because some chemical reactions produce gas. Right? So if you trap a gas in some sort of a vessel, maybe a water trap, where you bubble the gas from the reaction into a water-filled jar that's inverted, and it just displaces the water. Right? Then you trap the reaction gas. So this is not like standalone stuff. It's valuable for chemistry. Okay, let's see. Who's next? Avogadro's law. Okay, let's see. Let's erase that. Avogadro. Avogadro was Italian. So Avogadro's law is going to investigate the relationship between volume and amount, number of moles of a gas. So that means we have to keep pressure and temperature constant. And what he found is if you have, at a given temperature and pressure, if you inject more gas into a space, with these being constant, the volume will increase. So they're directly proportional. Okay? And of course, being a quotient, we know it's direct proportion. And if you, and this came in 19th century, actually. So it's like we're going century at a time to get each one of these laws. The plot, I thought I was going to show you a plot. It would be a straight line with a positive slope. The interesting historical item about Avogadro was this Congress or meeting of chemists in Europe at the University of Karlsruhe, Germany. The problem was that in chemical reactions, it was more like a recipe for chemists. You put this together with this and you get that. They didn't really know what was going on at the molecular level. And as a consequence, when something went wrong, they couldn't fix it. Now, for a college professor, you know, that damages your reputation. But for industrial chemists, you're losing money and lots of it. So they were desperate. They got together in Carlsbad and said, we're going to solve this problem. Well, they were there for a week or two and just threw up their hands, said, we can't figure this one out. Fortunately, there was a young chemist. His name was, two N's, and Cannizzaro. I think that's the way you spell his name. He had published a paper on reactions based upon the work that Avogadro did. And by this time, Avogadro has been dead. But his papers referenced Avogadro, and he was handing them out as people were leaving the Congress. I mean, he didn't have enough prestige to go inside, I guess. So he was just handing out his reprints. They took them politely. They took them and went back to their universities and companies and read it, and light bulbs started going on all over. So here was the reason. Here was the basis for that revelation. Avogadro said, after studying and using this law, after studying that law, he said that if you have, that's a sphere, not a circle. If you have two spheres of equal volume, right? Volume 1 equals volume 2, and you keep them at the same temperature, okay? And the pressure inside you measure is exactly equal. Right? So we have all these three factors are equal. He said, if that's true for gases, then the number of moles in this one are equal to the number of moles in that one. And that was a world-shaking revelation, something that simple. Now they knew that if they had a gas here and a gas here, with the conditions equal, then they knew that they had exactly the same number of particles of each gas. And the only thing that could cause a difference in mass between the two was the mass of the individual particles. Now they had a way to measure the masses of the particles, and then from that point they could measure any kind of mass once they had a reference point, and they could calculate how many particles were in here. Because what is a chemical reaction? Reactants, products. This is not mass equals mass. This is numbers of particles. So when you have a coefficient out here, you're saying that many moles of this react with that many moles of that to give you moles of this and moles of that. Now they had a way of relating moles, and their chemical reactions, their recipes, made sense. And they started solving problems all over the place. And that's one of the reasons that the chemical industry was huge in Germany for so long before America finally caught up and surpassed them. In fact, when I was getting out of high school, if you wanted to go into chemistry, you had to study German, because that's where all the interesting papers were being written. Now, fortunately, they're mostly in English or translated into English. Okay. So that's why Avogadro is so important. And you can make these relationships before and after. Anytime you have a before and after problem, you would use one of these ratios. Let's see, how we go on time? 3:15. Okay, we're good. As long as you can stay awake. Right? Is your knee bothering you?
Yeah.
Do you need to walk around on it a little bit?
No, I'll be fine. I'm just, it kind of hurts.
Are you taking anything for it?
Yeah, I just can't take it and do stuff.
Oh, okay. How about anti-inflammatories? Or are they frowned upon? Because they do thin your blood.
I think I couldn't have them before my surgery, but I think I'm fine now.
Yeah, okay.
I'm going to make a recommendation here, Tylenol and these, like I Advil together.
Mm-hmm.
There's studies being done now that show that they're equally effective at pain control and other medications.
They work together.
Yeah.
Mm-hmm.
I didn't know that.
So
Take 500 Tylenol, 400.
it's true. Okay. So I'm going to skip this for now. We've talked about stoichiometry, right? In chemical reactions, but we've only referenced it in terms of mass to moles, or I think we talked about concentration of solutions to moles.
Yes.
Okay. Now we're gaining access to reactions where we can convert to moles using gas laws. That way, and whenever you have a chemical reaction, in other words, you can't go anywhere in this reaction unless you convert to moles first. Right. So mass is easy. You just need the molar mass. Solutions are easy now. All you need is how much of it you have, and what's the concentration. You calculate the moles. Now, if you know pressure, volume, temperature, you can find moles. I'll show you how to do that in a minute. So we've got multiple ways, and some reactions, they're all gases, like this one. This is the Haber-Bosch process. Actually, that's in reverse. This is decomposition of ammonia. Reverse it, and you have the Haber-Bosch process. Okay. Now, before we get to the ideal gas law, I want to combine the gas laws. And the reason for that is we're still in the before-after scenario with this one. So we know that the relationship of pressure to volume is product, right? But we also know that the relationship from volume to temperature is quotient. And we know that the relationship between volume and moles is quotient. Right? So this is before. That's after. That's the combined gas law. Just put them all together. So now, if you want to investigate volume and temperature, but pressure is changing too, but you're holding moles constant, then you've got PV over T. And you can use that expression to, all you need is to know, let's see, in that case, you would have 6 variables, right? If you know 5 of them, you can solve the 6th one. So a more fluid, no pun intended, a more fluid experiment can be accommodated with the combined gas law. Okay, so that's before and after scenarios. The 3 gas laws and the combined law. Now, there may be situations where you don't know what it was before. You just know what it is right now, a state function. What are the conditions right now? We want to solve for an unknown. Right? So, we know that the combined gas law says pressure times volume and temperature times moles on the bottom, and that's going to be equal to a constant, right? Because each of these parts is equal to a constant. So this is sort of a composite constant for each of those. Right? So if that's constant, then all we need to know is what is that value. If we know what that value is, then we don't need to know the after. We just need to know the right now. Right? So we need to find out what this is. If we know what that is, then if we know 3 of these, we can find the 4th one. Okay? So it's usually solved in terms of keep the P and the V on this side, and then put the N and the T on that side. And this value is, this variable is given, or constant is given a special symbol, the R. This is the ideal gas constant, R. And, but this, you have to use the right units when you're using this equation. You can't do ratio things with any unit you want, right? So this one's going to be in Kelvin, temperature. This one's going to be in moles. This one's going to be in liters for volume. And this one's going to be in atmospheres for pressure. Okay? So if we put atmospheres and liters here, moles, the temperature there, then this K is going to have units of liter atmospheres per mole. K. Right? And if you know what R is, what that constant is, and look at the units of this will tell you what these units have to be, right? Because there are a list as long as your arm of different R's. It depends on the equation you're using them in. So in this case, if these are the units, then the actual, the magnitude, the number that goes with it is 0.08206, and that's liter atmospheres per mole. Okay, that's what R is equal to with these units. Okay, now that we know that, just plug that value in here, and then we need to know 3 of the others, and you can find the 4th one. Okay, so that's the ideal gas law. I'll leave it up there. But you need a better idea of what an ideal gas is. Sometimes it's called a perfect gas. I like ideal gas better. It remains a gas under all pressures and temperatures. That is, no matter how much pressure or how cold you get it, it stays a gas all the way down to absolute zero. Now, we know that doesn't happen. What happens to a gas when you get it cold enough under pressure? Yeah, well, it may turn liquid first. Sometimes it turns to a solid. Right? Carbon dioxide, right, makes dry ice. Let's see. Helium. I've not heard of a solid helium, so I think right down close to absolute zero, it stays a liquid. But others, nitrogen turns liquid at minus 195 centigrade. It's really cold. Whereas dry ice is only 78.5. So it depends on the gas. The ideal gas stays a gas always and forever. We also have to assume that the volume of the gas is 0. What they mean by point molecular volume is like, what's the area of a point in math or geometry? The area of the point is 0. It has no area. Right? You have to have 2 dimensions to have an area, and a point doesn't have it. Right? So we assume that the volume of a gas is a point volume. It doesn't have a volume of its own. It's just the space that the gas occupies at that time. What that says is that the individual molecules don't have a volume. They don't interact. Ideal gases do not interact. In other words, when they bounce off of one another, it's just like billiard balls. They don't attract, they don't repel. And of course, they have to obey all the gas laws. That's a given. Real gases. Now, here's what we really observe. Right? They liquefy or solidify if you get them cold enough, under pressure. They do have volumes. In fact, those volumes can be measured. And they do interact. Some interact by repelling, some interact by attracting one another. Especially polar gases. Those that have a dipole, like water. So water would not be an ideal gas at 1 atmosphere. Maybe at higher temperature, yes, but not at a lower temperature. So here's a restatement. Low pressure, high temperature, you can expect the gas to behave ideally. And that's relatively speaking. Some gases require really high temperatures to behave ideally. Some care less. Noble gases, they can do. Their high temperatures could be like minus 100 degrees centigrade. Here's the ideal gas equation. It was first developed conceived by Emil Clapeyron. I don't know. We haven't done the Clausius-Clapeyron equation yet. You'd know it if we did. Okay. So he has an equation named after him and one other guy. So there's your ideal gas equation, and I showed you how it was derived. This is the constant that we're going to be using in here. But eventually, well, I don't know if we do it in this course, but there's another version of it that incorporates the energy here, J, the joules. So the joules substitutes for liter atmospheres, but there's also a factor to convert one to the other. That's why this value is not the same as that. So liter atmospheres is not directly equal to joules. It has to be factored. Okay. So when do you use one or the other? Use the combined gas law or the individual gas laws when you have a before and after situation. You know the conditions before, you know some of them after, solve for the unknown. If you don't know the conditions before and after, if you're just given conditions right now, the ideal gas equation is the one you go for. And you can solve it a number of different ways. That's all this is. So what if we solved it for volume? Let's see which one's volume. Volume equals nRT over P. And we say, okay, what is the volume of 1 mole of gas at 0 degrees centigrade and 1 atmosphere pressure? So standard temperature and pressure, I didn't mention that yet. STP for gases is 0 degrees centigrade and 1 atmosphere. Just for gases. Later on, when we talk about standard temperature and pressure for other reactions like solids and liquids, the temperature changes then to 25 degrees. But for gases, it's 0 degrees. Okay. So at standard temperature and pressure, what is the volume of 1 mole of gas? Okay. So we have 1 mole here. We have our ideal gas equation, our ideal gas constant. Temperature is 0, which in Kelvin is 273. Right? And pressure is 1 atmosphere. So really all we have to do is multiply this times that and find out what the volume is. I already know what it is, so I don't need my calculator. So the volume turns out to be 22.4 liters. That's the volume of 1 mole of any gas under standard temperature and pressure conditions. Okay. So here's a kind of a problem. What's the pressure of a system when you have 2 moles of gas at this temperature and that volume? Well, let's see. Do we have everything we need? We need volume, temperature, pressure, and moles. Right? Volume. 50 liters. Got it. Temperature. Got it. Just need to convert to Kelvin. Moles. Got that. And the question is, what's the pressure? You can solve it. In this case, we're rearranging for pressure, and we fill in the values that we know. Right. Solve for the pressure. And it's 1.18 atmospheres. For this one, you've got to change this temperature to Kelvin, but you've also got to change that pressure to atmospheres, because the gas constant is liter atmospheres. You have to match the units. Otherwise, you're just spinning your wheels. Right, so in that case, we get almost 8 moles of gas under those conditions. Okay. So here's one where we're trying to do some stoichiometry. We want to know the mass of, Mercury 2 oxide needed to produce this volume, which is that many liters, of oxygen at this temperature, and which is Kelvin, and that pressure. So what do we need? If we need to know the mass of this, and this is what we're producing, we've got volume, we've got temperature, and we've got pressure. So now we're going to solve for moles, and that will tell us how many moles of this are produced. Then you use mole ratio of 1 to 2 to find out how many moles of Mercury 2 oxide. And once you know the moles, you can use the molar mass to convert back to grams. Okay? So I go through the whole thing here. That's the number of moles. There it is. That's the number of moles of oxygen, and then you convert it to the number of moles of Mercury 2 oxide. There we go, our ratio here. And there's the molar mass, and that's how much Mercury 2 oxide you start with. Okay? That's an old reaction. In fact, this is the reaction that was used to characterize oxygen in the first place. They just took this solid, heated it up, noticed it produced this plus a gas, and characterized the gas. I think Lavoisier did that. Okay, what's the Dumas method? Well, we're going to do it. So I guess we ought to study what it is. The Dumas method is a way of using gas relationships, these laws, to determine the molar mass of a volatile compound. Right? So you need something that has very low boiling point, like ethanol would be a good one, acetone, right? Some of those very volatile liquids. And you work from the premise that the molecular weight, or the molar mass, is equal to mass per moles. So the moles weigh this much. 1 mole weighs that much. So you need those two factors, right? So what you need is a container, because we're going to make a gas. You need a container in which you have vaporized your liquid into a gas. And if you do that and measure the temperature at which that occurs and the volume of the container and the pressure on the gas in that container, then you can calculate the moles of the gas in the container. Okay? So, got that one. Now, how about the mass of the gas? Well, if you have it in a container, say we're using an Erlenmeyer flask. We seal it off, and we have a liquid down here, and we heat it up in a water bath. So we know the temperature of the gas. We know the volume. Just fill it up with water and then measure it. Right? So the volume. And the pressure is atmospheric pressure. So once you've vaporized all of that liquid, and there's nothing but gas in here, then you take that container, weigh it. But before you did that, you weighed it empty. Right? So now it contains your gas completely filled, and you weighed it before and after. So now you know the mass of the gas, and you know the moles from the gas laws. Calculate the molecular weight. That's the Dumas method. Okay. And here's an example. In this case, what we're doing is we're taking this equation. Mass won't change, but the moles are like that. No, that's not right. Let's do this. Moles would then be like this, RT over PV. There we go. And then we're substituting this in here, right? So the advantage of this is you're doing it all in one calculation, right? Because we got this, that's a constant, we got the temperature, we got the pressure, we got the volume, we got the mass by weighing it. Then we just plug all those numbers in there, calculate the molecular weight. There you go. So the mass is going to be, let's see, mass on N. That doesn't look right. We've got mass per mole. Then we have mass over RT/V. Then the molecular weight would be that MeV over RT. That's wrong, isn't it? I need to remake that slide.
That is inaccurate, as they say in Washington. Misspoke.
they're saying it works, but I don't believe it. Okay,
I like the way you described it.
just like this. Yeah, I mean, that makes sense. It's mass per unit moles. So mass is on top, and what's moles equal to? Unless I solve this wrong. I did solve it wrong. Okay. Hold that there, take this and put it over here. Yeah, they're right, I'm wrong. So this would be RT. That's right. I was wrong. I made the slide, so I was right there, but I was wrong here. Okay. All right. So here's your combined gas law. We already looked at that one. So the question is, what type of problem is this? Final volume of some gas when 50 liters of the gas and this many is cooled to that and compressed to that. So you got a before and after, you got a before and after, you got a before, but you don't know the after. And the number of moles has remained constant. So what we're going to do is eliminate, we're going to eliminate the moles. Right. Here it is. They're equal to one another, so they cancel out. Okay, yeah, cancel those out. So that was a before and after problem. Okay. I'm going to let you work on this one in the review document. There are several examples in there for you. And we'll hammer on it. We'll hammer on it during the review next week. Okay. Dalton. Remember Dalton's atomic theory? He also played with gases. So Dalton's law of partial pressure is really very simple. You can measure the pressure of a pure gas or a mixture of gases. And you get a pressure total. He said the pressure, the total pressure in that container is due to individual pressures of each of the gases. So you got one gas in there, the second gas has its pressure, and the third gas has its pressure on down the line to however many. That's what partial pressure means. And you can also substitute in here the ideal gas equation for each one of the gases. So here we go. If the volume is the same, all these gases are mixed together in the same volume, so the volume is the same all the way across. Doesn't change. Number of moles is different. R is the same. T is the same. So really, the partial pressure is due to the number of moles of each gas. That was the point of this arrangement. Okay. Here we go. Now, notice that here we have this value as a factor, and this is the same value, so they cancel out. So the number of moles of individuals added together equals the total moles. And if we divide both sides by n, total moles, We divide through both sides by N total. Like that. Of course, this becomes 1. And these become fractions of the total, right? And these have special symbols. It's called the mole fraction. So the, sorry. The mole fraction then is a fraction is less than 1 of each of the gas. How many moles of each individual gas relative to the total? You add them all up and they're equal to 1. Let's see, here they are, one at a time. I've got them added together here. And also, if you want to know the partial pressure of each of the gases, all you need is the mole fraction times the total pressure. So if you know the total pressure, and somehow you can measure the individual pressure of the gas, you can calculate the mole fraction. Or if you have a way to measure the mole fraction, you can calculate the individual pressures. It's an equation. I like this one. We're going to relate mole fraction to the balanced equation. Okay. This balanced equation is nitroglycerin being detonated. Right? So you take nitroglycerin and it generates this gas, that gas, that gas, and that gas. So notice that you start out with 4 moles on this side. And this, they say it's a gas, but you know, most nitroglycerin I've seen is liquid. It's still very unstable. And you're going from 4 moles to 12, 22, 28, 29 to 29 moles, 4 to 29. And we know that from Avogadro, if you expand from a small amount to a big amount, you either increase the pressure to a huge amount, or at a constant pressure, you increase the volume. So that's where the explosive force of nitroglycerin comes from, is generating 29 moles out of 4. And we can tell the mole fraction of each one. All we need is the total moles here, which is 29. And then CO2 would be this mole fraction. And mole fraction of water would just be 10 divided by 29. And nitrogen, excuse me, nitrogen would be 6 divided by 29. And oxygen would be 1 divided by 29. That's the mole fraction in the products. Assuming all of this is converted. And I'm pretty sure it is. Okay, so these are conditions. What do we want to know? Calculate the pressure the nitroglycerin contained. Okay. So this tells you the volume in a 100-liter vessel at this temperature and that initial pressure. And the vessel expands to 110 liters and the temperature rises to 400 C. So we've got initial, final for volume. We've got initial, final for temperature. Volume, temperature, they change. And pressure, we're starting off at 20 millimeters mercury. We want to know the final pressure. That's initial. So we know initial, final here, initial, final here. So how are we going to tell? Well, we need to know moles. How do the moles change? Initial, final. Well, the moles change from 4 to 29. Right? So we can plug in 4, 29, Before and after here, before and after here, before, solve for after. Let's see, here it is. So these are initials, that one. This is final, 29, and temperature final. And then initial moles, initial temperature, and final volume here. And we get the pressure. So the pressure has gone from 20 to 297 millimeters of mercury. Quite a jump, 15 times. Okay. All right, so what are we doing here? The pressure of the system was this. Oh, that's the pressure after the reaction. Okay. So we want to know what contribution does each one of the gases make to the total? We just need to know the mole fraction. So there's 1229 times the final pressure. And that'll give you the contribution of each of the gases. So it looks like CO2 is the most, water is a little bit less. If you add them all together, they should be very close to the initial, within small error. Okay, last item of business, kinetic molecular theory. Up to this point, we've been talking about gas laws. We don't know why things happen the way they do. That's what a law says. So the kinetic molecular theory gives us an explanation for why things happen the way they do. And it's based upon a molecular model of gases, like they're small particles, and they got energy. They are moving. Okay. First of all, we have to assume there's large numbers of particles, huge amounts. Small amounts would be, we wouldn't be able to measure it, and the randomness would not be factored out. So large numbers of particles, very small particle size relative to the distance between them. And the particles are in constant rapid motion. I mean, really fast, like speed of sound, fast. And they do collide. They collide with each other. They collide with the walls of the container. And the collision with the walls of the container is how we measure pressure. All you need is to stick a probe in there that will measure that force of impact of the particles. So how does pressure increase? Well, you're measuring impacts in your meter. So the more impacts that are made, the higher the pressure. Right? So how do we get more impacts? Well, one way is you can pump more gas into it, increase the moles. Or you could squeeze it down. And that makes the same number of particles into a smaller volume, so they're more frequent collisions with your meter. Or you can increase the temperature. Now they're moving faster and hitting your meter faster, harder, with more energy. All those will increase the pressure. Of course, we have to assume that they're just billiard balls. They don't interact. Okay. So the problem is, how do we measure the average kinetic energy of a gas? Let me say this first. They're using E sub K for kinetic energy. I had KE for kinetic energy, E sub K. Each one of the particles has that kinetic energy. But what kind of averaging algorithm do we use to take account of all the particles? Well, the first thing you need to know is that the measure of temperature is proportional to the average kinetic energy all particles. This is true for gases, liquids, or solids. That's what temperature is measuring, the average kinetic energy. Now, we're not going to use temperature in this calculation, but I think you need to keep that in mind. So if we've got 7 balls, each one of them weighing 5 kilograms, and they're moving at different velocities. Right? So the 5-kilogram ball moving at a different velocity produces this much kinetic energy for each one. That's the slow one, this is the fast one. Right? So it's going to have more kinetic energy. That's logical. Now, if we calculate the average of that value of these velocities, we get 40 meters per second. So that's the average velocity. But if we take that average velocity and try to calculate the kinetic energy as an average value, well, we're not going to do that yet. First, we're going to take the average. This is the true average, the values to average for average kinetic energy. So we take those values, and that gives us 5,000 joules, the average kinetic energy. But if we take this 40 meters per second and plug it in that equation, what do we get? Okay. We don't get, oh, excuse me, backwards. If we take this and plug it in the modified equation, then we say, all right, this average kinetic energy should be related to that average velocity. But that's not the average velocity we get from here. So it gives. You know, which one is right? Well, if you want to know the average kinetic energy, you want to average these, don't you? But we can't calculate the kinetic energy of every individual particles. Right? We need another way. So what we need is a way to measure the speed of the particles, and then we need the correct speed, the average, a type of average speed, to calculate the kinetic energy from that value. Right? And the way we do it is called RMS, root mean square. So how do we do it? We take the square of every one of these values. So that'd be 100, 400, 900, 1600, 2500. Square them all. Then average them. So we square them first, then we average them, then we take the square root of that average value. That's what that means. So it's actually backwards. We square, average, take the root of it. And that will give you this value right here, root mean square. Now, where have you seen root mean square before? You probably don't realize it. Right there. That power outlet. Alternating current coming from that power outlet. It's not direct current. It's not a constant voltage. It goes up, it goes back down, up and down, up and down. So what you think you're getting out of there is like maybe 115 volts, but that's alternating current. The thing about it is, this is a root mean square average of the sine wave, right? So this is voltage, positive, negative, and you have 60 of these cycles every second. Right? If you take measurements along here and you root mean square all of them, then you get 115 volts. Turns out that the root mean square of alternating current works as if it were direct current, a constant voltage. Okay, that's neither here nor there. All right. So if we have a a particle's trapped in a box. In order to determine the energy of that particle, we have to determine its energy on 3 axes, right? 3 dimensions: height, width, depth. 3 directions. So if we do that, then the total energy is due to the vector sum, right? Y'all studied, you have physics? No physics? Okay. Short lesson. If you have, say, our particles here, and it's moving like that direction, you can break that down into an x and a y vector, right? So it's moving this fast in that direction, but it's moving this fast in that direction to give you the combined. This is the combined vector here. That's what we're doing here. We're adding the 3 dimensions. That's only 2 dimensions. But here we're adding the 3 dimensions for purposes of calculating kinetic energy on each axis, x, y, and z. That's all that is. So if we continue, then for a mole of particles, we just need to multiply the mole times that kinetic energy. And then the root mean square of the velocities, these right in here, are just like we did before. It's the mean, that's what that bar means. When you see a bar like that, I mean, you take the average of all of the x values in the set. Okay? And then we're taking the average of the squared values and then taking the root of it. So that's mathematically what I just told you in words. So all this derivation you don't have to know. What you need to know is how to use this, and this equation is in the useful information. So the root mean square velocity, which is this Greek letter mu, the root mean square velocity of our particles is equal to the square root of 3 times our gas constant times the temperature in Kelvin divided by the molecular weight of the particle. That's the whole, all of this condenses into that. So what that means is, if we know the molecular weight, we know the temperature, okay, we do interject the temperature for average velocity is the average kinetic energy is measured by temperature. So that's the temperature term here. And in this case, we use a different constant because there's energy involved. Right? So instead of liter atmospheres, this is 8.3145 joules per mole K is the R value that goes in there. All right, so what's the velocity of air? Well, we sort of have to take a weighted average of the molecular weight of air because we've got mostly nitrogen and oxygen in there. So the weighted average at this temperature, here we go. This is the weighted average of molecular weight for air. And it's just a prorating of dinitrogen, which is 28, and oxygen, which is 32. But it needs to be in kilograms per mole, right? Because the joules has buried within it kilograms. Remember, kilogram meter squared per second squared. And then we substitute values, right? So here's our 3, here's our R value, and I've already gone in and converted joules to the terms. Here's the kilogram meter squared per second squared there. Right? So that way we can cancel the temperatures, we can cancel the moles, we can cancel the kilograms, and what are we left with? Meters squared per second squared. And when you take the square root of that, you get meters per second, which is velocity. There we go. And we find out that the velocity, the average velocity at that temperature is over 500 meters per second. That doesn't mean much to me. So we convert it to miles per hour. 1,100 miles per hour. Okay, that's greater than the speed of sound. Or as fast as a speeding bullet. Well, some bullets. I think a 1911 is in the neighborhood of like 850 feet per second. Oh, that's miles per hour. Okay, so that doesn't work. Sorry, I digressed the wrong direction. But they're fast. Now, if you do the same thing, in this case it's air, if you do the same thing for helium, you find that in order to have this average kinetic energy equal, right, between the two at that temperature, the helium has to be traveling much faster because it doesn't weigh as much. Okay, Graham's law. I think this is the last thing. Graham's law. Graham's law.
Let's see. We've done, yes, we have.
We've done empirical formulas and molecular formulas from raw data. Like percent composition, you can do empirical formula. Then you need the molar mass determined by an independent method to find out what the molar mass is. The formula, molecular formula. This is one of the ways to do that for volatile compounds is to do my method. And that'll give you the molar mass. Another way is to use Graham's law, and that works for gases. You can determine the molar mass of a gas by comparing it to a known gas. So if you put two gases at the same temperature into a container, the lighter one will travel faster, right? Because the temperature is the same, so it's got to move faster at the same kinetic energy. So that means if you have a long tube, for instance, and you put one gas in here, and you put one gas in here, and you have some way to measure when they meet, right? Some way to visualize when they meet. If they meet over here, which one is the lighter one? That one. It's moving faster, right? And the ratio of these distances can be used to ratio the molar masses of two gases. So if this is an unknown and this is a known, then as long as you can figure out where they meet, then you can measure the distance traveled, form a ratio, and here we go. So this is the ratio. This V is not volume. I think it's velocity. Okay, so the ratio of their velocities is also proportional to the ratio, let's see, what's D? Where's D? Not going to tell me. I think this is the distance. Yeah, distance traveled. So the ratio of the distances traveled is inversely proportional to the square root of the molecular weight of each one. That just means that the distance that A travels, say this, is going to be large, which means that the molecular weight of B has to be the larger one. So that's also in your useful information. Let's see, is this going to show us an example? Yeah. If you put hydrogen chloride or hydrochloric acid on a wad, I think cotton is safe, and then you do the same thing with ammonia on this end, then when they meet in the middle, they form ammonium chloride solid, so you can visualize them, right? So you can see how far they went, and just measure the distance. And actually, this is calculating what the ratio of the distances are. So this is HCl, this is ammonia, and that's 1.463. So the ratio of the two is 1.463. If you ratio this distance to that distance, you'll get that. Or if you have an unknown, like this X, let's see, there we go. That's where they meet. We used to use to visualize the movement of air through a fume hood. We'd have a beaker of ammonia, household ammonia, and we'd set right next to it a beaker of concentrated hydrochloric acid because it fumes. So the fumes come up and they meet in the middle and form that ammonium chloride fog, and you can see it move through the hood. Okay. Graham's law can also be used, well, in this case, we're solving for an unknown. So if you have a selection, you can find out what the unknown is here, and you can pick it out of these. Graham's law was also used. It's called the rate of effusion. In other words, if you have a porous membrane and you've got two gases on one side and you put them under pressure, then the lighter one is going to move faster. So it's going to move through the membrane faster than the heavier one. And that way, you can separate them. I mean, even if they're separated only by 3 neutrons, 235 to U-238. That was one of the ways that weapons-grade uranium was purified. Because in the purified uranium product from ore, you've only got 0.72% 235, and it's got to be much higher than that to be weapons grade. So this is one of the ways that they did it. And I used to live in Oak Ridge, Tennessee, and there were a couple of plants there. And one was dedicated to this procedure, and it was unbelievably large building, a monster building. And it was just stacks and stacks and stacks of Teflon filters. They had to use Teflon because uranium hexafluoride is corrosive to stainless steel. So the invention of Teflon was absolutely essential. And they created these membranes and they purified it, just one after the other in stages. Now, of course, they use ultracentrifuges. It's more efficient. I mean, that's what Iran is using. That's why we snuck a bug into their system and crashed a bunch of their centrifuges. Okay, so the difference is very small. So you have to stack a lot of sequential filters together to get them separated. This is the plant, K25 in Oak Ridge. And it's heavily guarded, has fences and guards and dogs everywhere. But there was a perimeter road that ran around the fence. And it was so long, you could go on an afternoon drive just one time around. So that's what we did as a family. We have enough money for other types of entertainment, so we just hop in the car and drive around the plant. Okay, so we studied ideal gases. This is what an ideal gas is. Real gases, they have volume, right? And they do liquefy at low enough temperatures. They don't stay a gas forever. They do interact with one another. All these factors tend to skew their behavior away from the ideal. Well, this fellow, Van der Waals, put together an equation that had correction factors in it. Right? And if you look at this PV, let's see, P times V equals nRT. So these are the pressure corrections, right? The number of moles and this correction factor. And then this one is the number of moles and this correction factor. So my guess is that those correction factors, the A's and the B's, are specific to each gas and have to be determined experimentally. But these are not important for us. They'd be important for chemical engineers, but not in our case. We'll just use the pure, the ideal gas equation. Okay, I'm done. You probably wore out too. So we'll meet next week for review and the lab. And this is going to be the first time I'm going to check your lab notebooks to see if they're set up
Oh,
correctly.
yeah, that, I mean, why you said that.
I haven't given you those rules yet?
No.
Oh. Okay.
You covered very briefly on the first.
Okay. Lab notebook. Here's your cover. So you're going to have your name. You're going to have the class, like CH213, and the semester. Or you can put the date, whatever. Semester is probably better. That's on the outside. On the inside, when you open it up, you notice that the first page, this is the inside of the cover, right? So this first page, you're going to start numbering in the upper right-hand corner. You don't have to circle it, just one. So that's page 1. You flip that page over, well, and on page 1, you're going to have a table of contents. And under the table of contents, all you need is for each experiment that you do, just write the title of the experiment and the page number, where it starts. You don't have to put from to, just the page that it starts on. And then skip a line, put in the next one. Okay, so this fills up gradually over the semester. Now, flip that page over. Now you got 2 pages. Right? This one's going to be 2. This one's going to be 3. Okay? So every page in your notebook has to be numbered first in ink. In fact, everything in your notebook is ink, no pencil. And all the right-hand facing pages are going to be odd. All the left-hand is going to be even. And did you buy one from me? I think you should have 200 pages when you get to the end. They have to be that bound quadrilined. So what you'll do is maybe skip these 2 and go to page 4 and 5 and start on 5. Write everything that you're going to do here only on odd pages. Leave the evens alone. The evens are for big mistakes that you have to cross through and correct over here. Or if you have some things that you want to do over here, like draw a graph or do extensive calculations or create something in Excel, print it, cut and paste it in here. If you paste something on a page, then once you get it pasted, initially across the board, the boundary, right? So if it falls out or gets torn out, you know something's missing. So what do you put in here, right? You want to put everything in here that you're going to need to conduct the experiment and later to write the report. If you do this correctly, then you won't need the hard copy ever again. After you put it in here, you can write your report from your notebook. So you want maybe introductory remarks. You need a blurb on safety. You need materials. Okay. What do you need in the experiment? Right. Then you need a procedure. Step by step. Do this, 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 this. And then let's say we're going to go to the next page. So this is 4 and 5. So you're going to need data. So my suggestion is for your data section, look at the report and say, what values, what things am I going to get from this experiment? What information? And create either a table or a list
with blanks in it, identified blanks, so that you'll know that something needs to go in that space. The reason for that is, if you get down here, you're moving along in your procedure, and you get down here and you look up there and there's an empty space, you're probably thinking, uh-oh, what did I miss? If you go back and check and say, oh yeah, I know why I skipped that. So you just exit out or make a comment and say, we didn't need that. This is a record of everything you're going to do, and then while you're doing it, you make comments and observations. You may have observations. 5, 6, 7. We have other observations that you make in addition to the data. Then you'll have maybe pre-lab or post-lab or questions that need to be answered, right? And then you'll have summary and conclusion statements. What is it all? Oh, I left one out. Calculations. So you'll know how you actually dealt with the data. What did you do with it? How did it enter into any calculations that were done? Then you do a summary and conclusions. If you do it that way, and when you go in the lab, you'll know what you're going to do. You're safer that way. Plus, when you get ready to write your report, it's all there. It's just a matter of putting it in the right form, right? Using the correct language. Did I hand out? Well, let me see. Maybe I did. Maybe I did. I had brought some with me. Oh, maybe. Oh, yeah, yeah. Okay, good. This one. This one. Okay. I don't know if I handed these out yet or not. This is a report format. Then I've got, here's a sample. I'm going to give you a sample report. I removed personal information from it. Actually, it's a report. And this is my grading rubric. So you can see what I'm looking for. And then I've got unused rubrics. If you want to use one of these. Grade your own work before I see it. Do that. And then this one, it took a couple of years, so I finally realized I better say something about this. Maybe you don't understand what plagiarism is. Plagiarism is an essay. Yeah, that's it. Plagiarism in a lab report. Okay. So the whole point of a well-written and maintained lab notebook, it's a record of everything you do and everything that you've gained in the process. If you work for a company, they usually have you sign, if you're a scientist in a company, they usually have you sign a document that says, all my lab notebooks and everything I do in this company belongs to the company. So when you leave, they keep all of your records. And that's so the next person that comes in can follow your work. So you want your lab notebook to be readable. It doesn't have to be pretty, right? But all the information that you gathered in the process of what you did needs to be there so that either you or somebody else can go back in there 6 months or 2 years later and do the same experiment over again, exactly the way you did it before. That's one thing. The other thing is, and I hit on this before, you want to be able to write a report from this, not from the hard copy. Write a report from this. And you definitely don't want to regurgitate the procedure out of the hard copy. That'll be obvious. I mean, a dummy can figure that one out. I'll know if you're regurgitating, and you'll notice on that rubric, if I see that you've regurgitated the method, you get 0 points for that. There's also the way to express yourself in the procedures in particular. Okay, when you put your procedure in here, it's like do this, do that, do that. You're saying what you should do. But when you write your report, this part needs to be in third person, passive, past tense. For instance, say you weigh something out for an experiment. So you would say 13.5 grams of sodium carbonate was weighed into a plastic weigh boat using an analytical balance. Okay? Third person. You don't say I, you don't say you. You don't say we did. You say it was done. This was weighed. Good. That's third person passive past tense. I'm glad that's recorded so people that aren't here can see it. If you lose any of those, all of that stuff is in Blackboard. Or if you use that rubric to grade your own work, then you can always print out another copy. And when I look at your notebook the first time, all I'm looking for is that setup. You got to number all the pages, you got to label the notebook correctly, and you need a table of contents. That's it. I don't look at the particulars until the end. I'll grade them again at the very end. And don't worry about pretty. We want accurate, not pretty. Okay. I guess we're finito. Let me stop this so it'll start compiling. There we go.